Hello, I'm Seema and welcome to part 1 of the topic Acids and Bases in Organic Chemistry. You've studied about acids and bases in Gen Chem. In OrgoChem, the way we study acids and bases is not quantitatively, but we try to understand the structures of molecules and we try to find reasons why an acid may be stronger or why a base may be stronger or weaker. So instead of going into the mathematics of acids and bases, we try to give reasons, look at the structure of the molecule and give reasons why a molecule would be a good acid or a bad acid. Would it be acidic? Would it be basic? And how much of it? In comparison, which one would be more acidic or less acidic? But before we come to that stage, I would like to just revise what we know about acids and bases from our Gen Chem. There are 3 definitions of acids. It does not mean that these acids are exclusive of each other. That is, these definitions are not exclusive of each other. Although when you look at a chemical reaction, you may be using one of these definitions to explain whether the substance that you're talking of is an acid or a base. But they are not exclusive. You can use in the same reaction, you could explain the acid or the base using either one of the definitions. But you always reach the same conclusion because basically they are defining the same things, that is the acids and bases. So what are these 3 definitions? The first definition of acid is the Arrhenius definition of acid. According to Arrhenius definition, an acid is a substance that gives out an H positive ion in water. That is, in an aqueous solution, anything that gives an H positive ion should be an acid. And at the same time, in an aqueous solution, anything that gives out an OH negative ion in water would be a base. So this is the definition given by Arrhenius. The problem with this definition is that there are substances which act as acids and bases also when they are not in aqueous solution, when they are in some other medium. So this definition is limited only to aqueous solutions or acids or bases in aqueous solution, which does not always happen. Anyway, let us just take an example of this. For example, HCl, that is hydrochloric acid. HCl is an acid, or hydrogen chloride is an acid, and according to Arrhenius. And why is it an Arrhenius acid? It's an Arrhenius acid because when you put HCl in water, it dissociates to give H positive and Cl negative. Therefore, it gives H positive, and since it is giving H positive in water, HCl is an acid according to Arrhenius. A base, on the other hand, an example is sodium hydroxide. NaOH, when you dissolve it in water, it dissociates into Na positive and OH negative. And since it gives OH negative in aqueous solution, it is a base according to the Arrhenius definition. So this was Arrhenius acids and Arrhenius bases. A substance that gives out H positive in water is an acid, and a substance that gives out an OH negative in water would be a base. So we now come to the next definition, that is the Bronsted-Lowry definition of acids and bases. Bronsted-Lowry is a more encompassing definition. It is not limited only to aqueous solution. It says that anything, irrespective of what the medium is, anything that gives out a proton, not H positive. H positive actually is a proton. So he said that anything that gives a proton is an acid. And it's not necessary that it has to be in aqueous solution or in an aqueous medium. Anything that would donate a proton or a proton donor would be called an acid. And at the same time, how would you define a base then? According to this, he said it's not OH negative. It's not necessary because if you don't have water, you may not get OH negative. Or if the negative ion in the base is not OH, even then you may get, the substance may act basic. So anything that accepts an H positive, that is a proton acceptor, would also be a base. So the Bronsted-Lowry definition, I would like to repeat it, is anything that donates a proton in any medium is an acid, and anything that accepts that proton in any medium is a base. For example, you have HCl in ammonia. So it's not in water, it's in ammonia. So HCl in ammonia, it gives out its H positive and ammonia becomes NH positive, NH4 positive. So HCl dissociates into H positive and Cl negative, and the H positive is gained by NH3 and it becomes NH4 positive. Therefore, HCl is donating the proton and hence it's a Bronsted-Lowry acid, while NH3 accepted that proton to form NH4 positive. Therefore, NH3 in this reaction would be a base, a Bronsted-Lowry base. Now, when we talk of this, I'd like to take up another two examples here. Hydrochloric acid, when it reacts with or in aqueous medium with water, it reacts. HCl dissociates to give you H3O positive, that is H positive, and Cl negative, while water here is acting as a base. Why? Because water accepts that proton and becomes H3O positive. Do you notice? HCl broke down into H positive and Cl negative. It means it was a source of H positive, a proton donor. So the proton donor, according to Lowry-Bronsted definition, would be an acid. And the proton acceptor is water. So H2O becomes H3O positive. It accepts that proton and therefore, according to Bronsted-Lowry, this is acting as a base. Remember, at the same time, when an acid loses its proton, what is left after it loses its proton? What is left behind? What is left behind is Cl negative. So Cl negative, anything that donates a proton is an acid. So Cl negative is now negative, proton is positive, and Cl negative is negative. So it would rather accept a proton since it is negative. So when you have an acid, after the acid donates its proton, it gives rise to a base. After losing its proton, what is left behind is a base, and this base is known as the conjugate base. It is known as the conjugate base. So an acid, after it releases proton, gives rise to a conjugate base. At the same time, a base that accepts a proton gives rise to a more positive species. Now this was a base, it was a proton acceptor, but H3O positive has a proton, so it is positively charged. So in comparison to this is more acidic because it has accepted the proton. So after accepting the proton, it is H3O positive. Therefore, this is the conjugate acid. It is the conjugate acid. So we find that an acid after reaction produces a conjugate base, while a base after reaction gives rise to a conjugate acid. The conjugate is nothing but the resultant that is formed after that particular species undergoes a change. An acid undergoes a change, it loses a proton. So what is left behind is a conjugate base. A base accepts that proton, so what is formed is a conjugate acid. So that is one thing to be understood. The conjugate acid and a conjugate base. Let's take another example here. Ammonia reacts with water to produce ammonium ion and OH negative ion. So this can also be explained on the basis of the Lowry-Bronsted concept. NH3 is forming NH4 positive. If NH3 is forming NH4 positive, it means NH3 is gaining a proton. It is gaining a proton. Anything that accepts a proton is a base. So ammonia here is a base. Water, on the other hand, has donated that proton. So in this reaction, water is acting as an acid. Did you notice that water, although it's a neutral substance, in this reaction, it acted as a base, but in this reaction, it is acting as an acid. So with ammonia, water acts as an acid because it becomes the source of the proton. It gives out the proton. So when the acid gives out the proton, it produces the conjugate base. So what would the conjugate base of H2O be? After removal of H positive from H2O, H2O is nothing but HO NaOH. So when you remove the H positive, it means these two electrons of the bond, I should make the electrons rather. There are two electrons forming a bond between H and O and two electrons that are forming this bond. So when it loses H positive, it means it keeps the electron of hydrogen to itself and only the hydrogen is lost, and that's the reason why hydrogen becomes positively charged. And since hydrogen has only one electron and one proton in the nucleus, therefore what is left is only a proton, and that's why we call it the proton, the acid is a proton donor. So when it loses that, these two electrons are left with OH, and this one electron that it got from hydrogen gives it the negative charge. So when it gives it the negative charge, water on losing the proton forms the conjugate base, which is OH negative. Because OH negative is now rich in electrons, it would not act as a proton donor, rather it would act as a proton acceptor. And ammonia, which was the base, after gaining the proton, it forms the conjugate acid, that is NH4 positive. So these were definitions of the Laurie Bronsted and the Arrhenius definition. There's one more thing. If you have, just to keep in mind, we'll go into details of it later, or you would have done it in your Gen Chem. When you have a strong acid, the base that it forms is a weak conjugate base. If you have a strong base, it forms a weak conjugate acid. But if you have a weak acid, it forms a strong conjugate base. And if you have a strong, weak base, it forms a strong conjugate acid. Just keep this in mind, and I'll go into these details at a later time. Let us now come to the third definition of an acid. The third definition is a Lewis acid. It does not talk of either the proton or the aqueous medium. Now, sometimes you do not even have a hydrogen in an atom, and yet the substance may be acting as an acid or a base. So how do you explain, if there is no proton also, how would you identify whether it's an acid or a base? So this definition, Lewis, was even more encompassing, and it said that it was actually a broader definition of an acid and a base. So he said that an acid is an electron pair acceptor. Remember, a proton is positive and an electron is negative. So just to memorize, if a positive substance, donating a positive substance is acidic character, obviously the opposite in the case of negative charge should also be acidic. So if a proton donor is an acid, an electron acceptor should also be an acid. So donating positive charge or accepting negative charge should be the same thing. So we say Lewis' definition tells us that an electron pair acceptor would be an acid, while an electron pair donor would be a base. So anything that is deficient in electrons, that is positively charged, which readily accepts electrons, would act as an acid. And anything that has excess electrons, is negatively charged, would tend to lose those electrons, and hence it would be a Lewis base. Now, examples of Lewis acids and Lewis bases are AlCl3, cobalt 3 positive, magnesium 2 positive, BH3, BCl3, H positive. All of these are electron deficient species. And Cl negative, F negative, even a pi bond, the electrons of a pi bond, OH negative, all of these are electron rich species, and they tend to donate these electrons, and therefore these are electron pair donors, and they act as bases. And all of these that are electron deficient, they are known as Lewis acids. An example of this Lewis acid-base reaction is BF3 combining with NH3. Here, the BF3 and NH3 are combining, and there is no H positive being formed. It is this lone pair of electrons on nitrogen which is being shared here, and therefore the nitrogen acts as the electron pair donor in this case, an electron pair donor would be a base. So ammonia here acts as a base, while BF3 accepts the pair of electrons and hence acts as an acid. So this is the Lewis definition of acid. As I told you, that these definitions are not exclusive of each other. It is not that if a substance is an Arrhenius acid or a base, it cannot be defined by Bronsted-Lowry or by Lewis. Different students may use different definitions depending on what they can really locate and pinpoint and really find. But whatever definition you use, you actually come to the same conclusion. So I'll just explain why. If you really look at all of these definitions, H positive is positively charged, proton is also positively charged, is H positive only, and electron pair acceptor also has to be positively charged. Anything that accepts negative charge should also be positively charged. Therefore, we find that all acids, irrespective of the definition, are positively charged, or they are electron deficient. And all, on the other hand, whatever be the base and whatever be the definition that you're using, all of them are actually accepting, they are accepting positive charge and donating negative charge. So you could say all of them are basically negatively charged. And since they are negatively charged, all bases, whatever definition you use, are negatively charged. And all acids, whatever definition you use, are basically positive in their charge. They are positive and bases are negative. Let us take this one example. OH negative combines with H positive to give you water. Alright, this is the opposite of the dissociation of water reaction. Let us take an example, NaOH and HCl, a neutralization reaction, a reaction between an acid and a base, which gives you water and a salt. And we are just taking a part of this reaction to study the different definitions. The OH negative from NaOH breaks down in water into Na positive and OH negative. And HCl breaks down to form H positive and Cl negative. Right? So Na positive and OH negative, H positive and Cl negative. Now these NaCl forms the salt, but OH negative and H positive will combine to form H2O. Here OH negative, when this broke, sodium Na positive was formed. It means the electron of sodium has come to OH negative. So this pair of electrons is, there is one negative charge. This pair, the red pair of electrons, is the one that is ready to, since it is negatively charged, it's not very stable and it needs a positive charge to neutralize itself. So it attacks the proton here, and when it attacks the proton here, what is it doing? The OH negative is attacking the proton and this pair of electrons is used, H was positive, and as soon as it combines with the OH negative, the one electron goes to H, the positive charge is neutralized, and as soon as the negative charge loses one electron, it is also neutralized and we get neutral water molecule. Now, how do we explain this reaction on the basis of these definitions? The first definition is the Arrhenius definition. According to Arrhenius, the OH negative, anything that gives OH negative in water is a base. Therefore, NaOH dissolved in water to give us this OH negative. Therefore, you can use this base, can be defined as an Arrhenius base. At the same time, HCl dissociated in water to give you H positive and Cl negative. Therefore, H positive is an Arrhenius acid. Right? So that was the first definition. The Bronsted-Lowry definition is that a proton donor is an acid and a proton acceptor would be a base. Now, HCl is the source of the proton. It was donating the proton. right? So H positive, the source of proton is HCl, therefore HCl was the acid. And who accepted the proton? The OH negative of NaOH? So this is the proton acceptor was OH negative, therefore this becomes the base in this final resultant reaction. So H positive, the source of proton would be the acid, that is HCl, and OH negative is the base which accepted the proton. So that was the Laurie-Bronsted definition. And the Lewis definition can also be used to explain the same reaction. You have this lone pair of electrons here, a pair of electrons, and this pair of electrons is attacking, is being lost. So OH negative loses these electrons, the electron pair, to form a bond with the electron pair acceptor, which was H positive. And this pair was shared equally by both oxygen and hydrogen to form water molecule. That is to form this red bond here. So according to Lewis, the electron pair donor would be a base, and the electron pair acceptor was H positive, therefore it was an acid. So did you see? Whatever definition we used, in each case, OH negative is a base, H positive is an acid here. So whatever is the definition, the fact that an acid is an acid and a base is a base does not change. So that fact remains, and you may use any definition depending on looking at the reaction. How do you explain that definition? So this was about the basic definitions of acids and bases. And now in the next video, I'm going to talk about the Ka value and the pKa value, a little bit more about Gen Chem, and then we'll move on to organic acids and bases. Thank you for watching. If the video helped you, please like it, subscribe to my channel and recommend it to your friends, and please return for more videos in chemistry. Bye-bye.